Okay, everybody. Good morning, good evening, good afternoon, depending on where you're joining us in the world. Welcome to what I guess is the second week of our technically spring break in this COVID era. MIT is starting the second semester, the spring semester, a little bit later. So we're technically in our spring break, so we won't have one during the semester. I'm Brian Anthony. I'll be your host for today, but really the star of the show are Greg and Ivan. But more broadly, just to put a little bit of context on the work that they've been doing, MIT right now has a surveillance study ongoing, which is a collaboration in the end between MIT Medical and the Clinical Research Center. And it's to study the relationship between vital signs, early indication of are there signs in the vital signs before COVID sets in. And this has been ongoing for a while on campus. There are opportunities for people to enroll and get involved. And Greg and Ivan have been working with MIT Medical, with the Clinical Research Center, with myself and others to deploy technology that is going to give us some additional visibility into vital signs. And then hopefully we'll learn how they are impactful or not to the operational needs of COVID or into human health in general. So Greg is a postdoc in the department, and Ivan is a doctoral student in the department. They also happen to be in my research group, so I know them quite well. But Greg and Ivan, thank you very much for your time today, and I'll turn it over to you.
Okay, great. Thank you, Brian. I'm just going to share my screen. Can't tell if I'm screen sharing.
You are screen sharing. It's not full screen yet, though.
Okay. Okay.
There it goes.
Yep. So yep, great. So quick agenda for today. So we'll kind of introduce the whole study and what we're doing, why we're doing it. We'll quickly go through what vital signs we're going to be measuring and why we think it'll be important. We'll take a look at some similar study results that came out late last year regarding wearable vital sign tracking. Then we'll talk about how we're collecting the data from wearables and from self-service kiosks. Then I'll also talk about some possible future applications of the hardware we're working on, then tell you how to join the study. So kind of at a high level, we want to look at COVID pass users on campus, and we want to track their vital signs using both these Garmin wearable devices and self-service kiosks with the goal of creating vital sign baselines for our users and to explore whether variations from those baselines can help us detect COVID early. And learnings from those we might be able to use as an enhanced self-attestation procedure going forward. Craig, if you want to.
Sure. So there's been quite a bit of research that's come out in the past few months on showing that wearables can in fact really help with early detection of COVID. And on the bottom, on the left here, I'm just showing an ROC curve showing from one of the more recent studies showing the sort of the true positive rate and the false negative rate for using a wearable with symptom monitoring as well. What you can see here is that straight line with the dashed would be completely random. And the blue line is showing the result. The solid blue line is showing the results with the symptom monitoring and wearables. And what this is showing is essentially that you can actually have some good indications from wearables. And it's, this has shown enough promise that certain wearable developers like Whoop, the Whoop strap that I'm showing on the right, are even advertising this as a feature. So this is just showing this is from their app showing your respiration rate. And this is from a user who had COVID, and you can see an increase in resting respiration rate. So it'll be interesting and useful for research to collect some of this data if people get sick with COVID, as well as monitoring the vaccine immune response as as the vaccine sort of starts to get widely distributed in the next couple of months. Can you do the next slide, Evan? The other motivation for this is sort of the current standard of care is temperature screens, which aren't that great at detecting COVID. And that the fact that we might be able to sort of enhance this screening by using both heart rate, respiration rate, heart rate variability, and looking at those trends. And we are fortunate enough at MIT to have twice a week testing of COVID, but that's not true for everybody. And that this could sort of be a stopgap measure to cue people to go get a test if they're unwell. And there's been a lot of data and studies showing that essentially what's more important is not sort of the accuracy of COVID tests, but is sort of the frequent testing and removing that population, moving the infectious population from circulation. So I think there's a lot that could be done to leverage some of these devices to helping stop the spread of COVID. And then the next slide, I'm going to hand off to Ivan to go into some of the details of the vital signs that we're monitoring.
Sure. So this is just an overview of the data that we'll be collecting and kind of its relevance. So most important, heart rate. And what's important to note about, I guess, most of these is that they're really all only relevant to a person's own baseline. So we won't really see a kind of interesting data until we've collected quite a bit of information about each person. And so elevated heart rate is typically seen in the studies that we've looked at relative to a person's baseline when they get sick. Now, the clinical way to take heart rate is using ECG, which basically measures voltage potential differences across different parts of the body. In our case, we're using wearable devices, which uses a technology called PPG, which basically relies on the fact that blood tends to reflect red light or absorb green light. And so using a red or green LED to shine a light onto an area like the wrist or the finger, and then measuring the amount of light reflected can kind of give you an idea of the pulse rate. And you can also get the same information by measuring chest displacement. In a clinical setting, this can be done with many different devices like strain gauges, motion sensors, impedance sensors. In our case, we'll be using a radar system to basically send out pulsed signals toward a person's chest, and then doing some data processing to extract the heart rate. So related to heart rate is heart rate variability, and this is the beat to beat difference calculated in milliseconds of heart rate. And there's all sorts of applications of this in clinical settings, but in general, a lower variability is linked to kind of a state of stress or infection. And there are different ways to calculate this as well. So respiration rate, normally measured using some kind of a mask device. In our case, it's being inferred from the PPG readings, because the breath patterns will actually kind of alter the heart rates in a certain way, and such that we can extract or the device itself can extract it and give us an approximate reading. And again, with the chest displacement, using radar to extract those breathing frequencies. Then we have blood oxygen level, which is kind of something you hear a lot about in regards to COVID. As lung function gets impaired, we tend to see lower oxygen in the blood. This is again measured using PPG, but a slightly different version of it, which includes an infrared light emitter, basically relying on the fact that oxygenated blood absorbs more infrared and less red light, whereas deoxygenated blood absorbs less infrared and more red light. And so calculating these ratios, the device is able to give us an estimate of the blood oxygen level. Again, temperature, self-explanatory, is usually elevated during an infected state. again, it depends on time of day and the person's kind of characteristics. And so again, this will be relative to a person's accumulated baseline. In our case, we'll be measuring it with a thermal camera, comparing the person's facial temperature relative to a IR reference emitter. We'll be looking at sleep duration and cycles. And there isn't great data relative to sleep cycles and COVID itself. This is this is a plot from the study Greg mentioned earlier, basically showing that it's not much different than just random chance. But there is some evidence that shortened sleep increases resting heart rate. So this can be a way to correct for increases in heart rate that are not related to COVID. And the sleep cycles effect is not known. In general, there's kind of three main sleep cycles: light, deep, and REM. They're in a clinical setting measured using by looking at differences in brainwave activity and eye movement. But in the consumer case, it's kind of an estimate based on sensor data from motion, from body temperature, and from heart rate. And finally, we'll just be looking at overall activity of the person, seeing how less movement might be able to indicate fatigue, which is something present during illness onset. A couple of interesting studies that have come out last year. So Stanford used mostly Fitbit devices and measured heart rate averages, steps, and sleep duration to basically conclude that they can predict around 2/3 of COVID-19 cases prior to symptom onset, with some going back as far as 9 days. And in their case, they created kind of a baseline profile for each user of 28 days long. And then if the user's daily curve sort of didn't match their previous average curve for the last month, they would flag that as an anomaly. And so in these charts above, you can see where the anomaly flagging starts for this particular user, which was about a week before the symptom onset. Fitbit did a study on their own as well, and they came up with this interesting chart here that shows here's day 0 with the start of infection, and we can clearly see respiration rate and heart rate both go up quite sharply, whereas the heart rate variability, or the beat to beat difference, tends to drop. So this is something we'll be expecting to see. Huami, which is another mobile wearable manufacturer in China, they looked at a very large kind of population of users, and had a similar kind of anomaly detection process where they looked at heart rate and also sleep duration in order to correct for the previously mentioned increase in heart rate due to shorter sleep. And they were basically concluding that with this anomaly detection, they could see population-wide kind of COVID spikes before official reporting sources would basically show that. The official sources here would be in blue, and the anomalies shown in red. And so we're hoping to build on all of that with our twice a week testing, with the COVID pass, and all the vital signs that we mentioned.
All right, so I've been working primarily on the Garmin and wearable side of the study, and we are about to distribute about 1,500 of these Garmin watches to people of the community for health monitoring. And I've got one on my wrist here. If you look at the computer, and it has a PPG sensor here, so I'm going to just show you that. You can kind of see the flashing green lights there. So that's recording information from heart rate, which it will infer some information about respiration rate as well. But so we are sort of very fortunate that we have such frequent COVID testing at MIT, and we are in a very unique position to correlate a lot of our this wearable data with ground truth test results, which a lot of these previous studies have not done. And I think that some of these studies may be more biased towards reporting more symptomatic or severe cases. So we have this device, the Garmin wearable, but we have to figure out how to actually get the data from this device. And there are a bunch of requirements in terms of data storage and not wanting to be locked down to future changes in format of the data. And then also storing this data in a de-identified manner so that we don't have to worry about issues with data privacy. Could you go to the next slide? So I built, oh, sorry, back one, yeah. So I built an app for taking this Garmin data. So what happens is we have this system called REDCap, which is a system for consenting users for studies. So if someone's interested in the study, they can click on an enrollment link and they'll go through sort of a typical consent form and enter in some health information. And this will be all stored on REDCap's very encrypted and compliant, potentially HIPAA compliant. If Kathy's on, she can correct me on if it's not HIPAA compliant, but it's set for the correct regulations for storing health data. Once that's done, it will generate a unique subject ID to that person, but that isn't associated with any person identifiable information, which will pre-fill a form for our website. And then with that subject ID, we'll perform a handshake with Garmin Health, which will give permission, thank you for pointing on this, which will give Garmin permission to send us data. And so once that's set up, Garmin will now continue to send us data from your wearable device, which will get pushed to our server and then dumped to a Google bucket. And finally, when the study's over, there's instructions for deregistering, which will disconnect the data from, disconnect Garmin from our symptom monitoring website, and will no longer get your data. So the nice thing about this is that the way that we're all storing this on our Google Cloud Storage, which is encrypted, all the stored data is de-identified and is only identifiable by a subject ID, which we can't actually correlate to anybody's name. Could you go to the next slide? Oh no. So we wanted to make this so since we're gonna have 1,500 people that we could potentially recruit from, we wanted to make this as simple as possible. So if you finish your REDCap, this is just a couple screenshots from the app. Once you finish your REDCap enrollment, you'll be sent to a link that will ask you to register, and it will be automatically filled with some subject ID, which will then, once you click that, it will prompt you to just enter your email that's connected to your Garmin Connect account, and you'll click agree, and then you'll get some instructions on how to leave the study when you are done. And that's it, and you're enrolled, and now we're collecting data that we can use for monitoring symptoms. I'm going to hand it off to Ivan, who's going to talk about the more exciting, cutting edge contactless ways of vital sensing.
Okay, yeah. So on the other side of this, we have the non-contact portion, and for this we're constructing sort of a modular instrumentation platform that we can deploy around campus. And in this iteration for the study, we're particularly using an IR camera to track temperature and the radar system mentioned earlier to extract heart and breathing rate. In the future, this platform will be augmented with possible instrumented flooring, like you see here for gait studies, and will be used to conduct additional radar software development. So it's constructed using a modular aluminum framing system with plenty of space, both in the front and the rear for mounting of various sensors and computers. For this current study, the hardware is built around a small PC with with a screen for user interface, using a barcode scanner to start the process. We're measuring ambient temperature. Again, as mentioned before, using an IR camera to measure the user's temperature, a radar board to collect heart rate and respiration rate, and an adjustable platform to adjust the height for different users. So this is a preview of the user interface. So we have kind of large pictorial labels explaining which phase of the scan the user is in, large flashing instructions, as well as a camera display on the bottom that shows the user's position in the pod. And so this would be an instructional page. This is during temperature scanning, so they can kind of see themselves. This is during the radar scanning. And here's just a very quick sped up demo video, just showing what the process would be like. Let me play this. So it comes in. And then as far as future applications of this platform, one possible expansion is on radar motion studies. So directing users to do certain tasks, and then collecting radar data based on those. And the application here is, in particular, something we're working on is instrumented homes for seniors, to be able to track different activity or different events without the use of cameras, to possibly alert in case of falls or anything like that. And then another application that is going on in our lab is gait analysis. And the way a person walks can actually predict different types of health conditions, especially in older individuals. And so adding an instrumented floor to this platform, and then having some directions as to what to do will be kind of a test that we can run. And so as far as the overall timeline, we're finalizing building these kiosks and the software and distributing wearables this month, and the first week of March. And then we'll be collecting data for about 12 weeks. And we hope to have something closer to the summer in terms of interesting results. So, yep.
Greg and Ivan, so I send you the virtual and the physical clapping, both for sort of all the hard work that you've been putting into this and for the talk. I guess the one thing I did want to add is highlighting this is a collaboration between MIT Medical and the Clinical Research Center, and we're supporting that community, which is supporting us as a community. But it also does hinge on the top of a collaboration with, as Ivan mentioned, a company called Sekisui House in Japan, which has been a gracious sponsor of looking at how these technologies, at least the ambient, the non-contact pieces, can be used in the homes. So I do want to recognize their gracious support and collaboration and bringing some of these pieces into fruition. So I want to turn it over to questions for the audience. I think put your questions in the Q&A. I think we previously had to disable the chatting function because of some bad actors in chat. But please ask the questions. And I think yeah, I don't think you can raise hand. That I don't know. Might be able to. But you use the Q&A. But let me just kick it off with sort of talking. That's my own question here. How is the sort of the Garmin and sort of ambient data used together? Is it acquired at the same time? Is it synchronized, or what's your thinking, Greg or Ivan, of the importance of being able to do synchronous or not?
So all of the Garmin data is time stamped. to UTC. I'm not sure if it's at the sort of the level of, and it's synced with GPS time as well. So it should be timestamped and correlatable to the pod data. My one open question is I'm not sure if it's actually recorded natively on like a resolution of sort of, you know, the second scale that would be more relevant to the pod acquisition.
Great, thank you. Question came in, is how consistent is the heart detection rate and correlation to COVID? Ivan or Greg, I'll let you figure out who wants to take that one.
I can go back and look at some of the studies that that we showed earlier that had the ROC curves, which basically shows the false alarm rate versus the. I always use the radar terminology because I find the specificity and sensitivity hard to remember. But that shows the rate of sort of a false detection versus a misdetection. So sorry, the long answer is I'd have to go back and look at the study.
Well, and also that's one of the things that we're hopefully going to be learning as part of this study, because I think, as you said, Greg, you know, as far as we know, this is one of the few studies that actually has the more ground truth, I guess, of the testing.
Yeah. Yes. I think almost all of the previous studies have been for self-reporting of COVID. So there's quite a good chance that you've missed mild symptomatic and asymptomatic cases in a lot of the prior studies.
Knowing that we have potential students and others on this call, or that may be watching it, taking a step back for a moment, how have you found sort of the process of doing human subjects research? I know, so you didn't necessarily have a lot of a background prior to starting this project with, so that wasn't sort of your fundamental training. So what have you felt has been sort of the pitfalls or the struggles that you've had to go through to understand the context of how to deploy technology when working with human subjects? I'd like to ask about both of you, actually.
Evan, you want to take that first?
I mean, I think again, I've kind of I've just started on this recently, but it's like a lot. To me, the experience is just there's so many moving pieces that have to be agreed to and put in place for something like this. So it's just it's just like managing all of that and kind of everyone's input and goals in this.
The other thing I'll add is that I think doing human subject research coming from a very different field is very illuminating to how much larger companies get away with doing analysis of data, and the ethics that you really should follow in doing that is much stricter than you would do at some of the big FANG companies. Just a question from Teresa. Will the system be reliant on MIT COVID Pass and the kiosks? I think for the Ivan, correct me if I'm wrong, the passes for the kiosk where it's set up so that you will tap in with an MIT ID, correct?
Yes, that's right. Yeah. It's independent of COVID Pass, but it does require MIT ID.
And I see another question, what type of analysis? There's a ton of analysis that Ivan could talk about on the radar side, but on the wearable side, it's just going to be a lot of anomaly detection algorithms, sort of stuff that's used for spam messaging that you can apply to some of these. So essentially establishing what is the statistical distribution of these various health, of your baseline health, and if you're off of it. We could also set it up as a supervised learning problem too. Since we'll have COVID data, we can actually bin data into healthy and COVID positive data.
One of the other questions here is, I actually probably should turn it over to Ivan to talk a little bit about the algorithms as well on the radar data.
Yeah, so it's a little bit early on the radar, but essentially what we're doing is we're collecting. Let's see here if I can find this. Essentially, we're collecting raw data from. In our case, we're using a TI radar card, a radar antenna, and later on we'll be trying kind of different approaches to extract the heart rate and respiration rate. At a high level, here we go. This is kind of like a setup here. At a high level, we're basically doing sort of Fourier transforms to extract the fine motion of like in this case here we have just a plate that's simulating a breath oscillation, and here's a preview of kind of an out of the box demo using the TI cards. So I guess to answer the question, at this point, it's still pretty early on in this process.
I'm going to take a question that came in from the chat. We have one in the Q&A, but let me go to the chat one first. How frequently do you expect a subject to use the kiosk in order to obtain reliable predictions? Daily, weekly, several times a day? Ivan, you want to take that one?
I think we'd love it if users frequented them as often as possible, mostly because temperature and heart rate tends to vary throughout the day, and whether you've exercised or if you've eaten, and so maybe 3 times a day would be kind of an ideal starting point to get an idea of what the daily differences are like.
And just put this in context for a moment. One of the original, an early sort of line of questioning when campus was in medical and the clinical research center was thinking about this, was asking the question, what if we actually, instead of having people wear wearables, what if we had these stations conveniently located broadly across campus, so that as you walk down the hall, that such a kiosk is never more than half of an infinite corridor away, so that it would be easy to either at the entrance to buildings, not wanting it to be a bottleneck, but sort of I think the better data for this study that we'll get, the more frequent data, not necessarily better, the more frequent data we'll get certainly is because of the wearables, but being able to understand how that information can show up in agreement with the pods, the kiosks, and then what is the right frequency if they were used in a different scenario. And these will first, I guess I'll also want to call out and thank Sloan. They're helping to deploy into the Sloan buildings the kiosks to start to do some of that research. But again, this falls under the entire MIT study, but Sloan in collaboration is really helping us to action on amplifying what we can do in the study. Let's see, one of the questions, I'll turn this either to Greg or to Ivan. Do you use any machine learning algorithms in conjunction with the wearable to filter out false positions? I think they may mean false positives, but maybe false positions. If so, which algorithms?
So we haven't we've only collected a little bit of data from lab members that we can't really actually do any work on because of that people weren't consented with that data. That was mostly to check if the data sort of exists. So we actually haven't been able to play around with the data and actually apply specific algorithms to it yet.
And then to clarify question. Oh, for our external attendees, how long is half an infinite corridor? That's good. I think the infinite corridor is what, 500 feet? Nah, it's got to be longer than that. How long is the infinite? Infinite corridor is the long corridor down the main complex of MIT. The light shines through it at least once a year, direct end to end. But it's actually, let's see, what is the actual length? 800, maybe 800 feet or so. It's about a 5-minute walk. It's under a 5-minute walk. Absolutely. Greg, go ahead.
The other thing I'll say, that the other sort of research contribution of this work is that understanding what someone's baseline is not a very well-defined answer, and it's actually very hard to get. As a researcher, it's very difficult to get sort of day-to-day or hour-to-hour variation of this data. So one thing that we're hoping that we could do with this study is also just make that data available to other researchers in the future for other algorithm development.
Okay, so I think with that, Greg and Ivan, thank you very much. Attendees, if there's any last question, please go ahead and post it now. Otherwise, look for, certainly for the MIT community that's on the call, please sign up. We have this session, we had an IEP class, we'll have some more information sessions, MIT Medical will, CRC will, the Clinical Research Center, to further inform the community about the opportunity and what we're doing. So look forward to your participation. But again, Greg and Ivan, thank you again for the talk and for all your excellent work in bringing this technology into reality. I think with that, Teresa, if you can bring up our exit slide. So this is again the last week of our spring break. Next week the semester starts, the spring semester starts, and we'll have Professor Neera Jain, an alum from the department, speaking about enabling human-aware automation, a dynamical systems perspective on human cognition. So I invite you back to the start of the semester next week, and same time, same channel, and for the next MECI Alliance seminar series. And as always, we try to cycle through having an on-campus presentation from a student or a postdoc, a faculty member, and then an off-campus company leader, industry expert, or yourself. So if you would like to make recommendations, either of yourself or of others, or have ideas on the types of things that you'd like to hear about, please drop us a line. We look forward to hearing from you and to seeing you over the next Wednesdays at noon. So again, thank you, Teresa, Irina, thank you, Greg and Ivan. Thanks again. Everybody have a good day.
Great. Thank you, everyone. Have a great week.